Chapter 4.3 Force due to magnetic fields. In the last chapter, we learned that current may produce magnetic field. In this chapter, you will see magnetic field and current interact to produce a magnetic force. Let's begin. Battery car. Check out the video to see how it works. Well, the two-wheel car moves itself. This is a simple device that converts electrical energy in the circuit to kinetic energy of the car. So, it is a motor. 1. Magnetic force on a current-carrying conductor. A current produces a magnetic field, which deflects a compass. By the third law, there should be a force on the current by the magnet. We should even say the current-carrying wire moves if the magnet is fixed, if the wire is light enough. Experiment 4D. The magnetic force on the current-carrying conductor. In the following setup, the magnet is fixed. It provides a fixed magnetic field. A current-carrying rod in the magnetic field will experience a force. Let's see what happens.
Set up the Fleming's apparatus. Switch on the power supply and watch for another motion of the rider. Repeat by turning the magnets around. Repeat by reversing the current.
So, as expected, when the current flows inside a magnetic field, the current-carrying wire will experience a force. In the video, you can see that the current, magnetic field, and the induced force on the current-carrying rod are at right angles to each other. In other words, they are mutually perpendicular. In the school laboratory, we may also demonstrate their relationship using a simple setup as shown. In this case, when the magnetic field points to the right and current flows in this direction, then the induced force will be upward. A. Feynman's left-hand rule. There is a relationship between their directions. The Feynman's left-hand rule, or simply called left-hand rule, helps us to memorize their relative directions. The pointer points in the direction of the magnetic field, from north to south, while the middle finger points in the direction of the current. And in this case, the thumb will tell you the direction of the induced magnetic force on the current-carrying conductor. Example 7. Applying Feynman's left-hand rule. This is a simple application of the left-hand rule. The crosses represent a magnetic field that points into the paper, while the current flows along the blue arrow, and hence you may apply the left-hand rule like this, and find that the induced magnetic force given by the left thumb points bottom right. B. Factors affecting magnetic force. The induced magnetic force will be stronger if the current is larger. The magnetic field is stronger. Or, let's find it out using the following setup. This is called a current balance. Note that there is a short insulator P, so that current can only flow from X to Y through the arm RS. When current flows from R to S, there will be a force on RS and upward force. Try it yourself. Since RS is pushed upward, the opposite arm QT is pushed downward. The balance reading increases as a result. In other words, the increase in balance reading is directly proportional to the magnitude of the induced magnetic force. If Sy equals Yt, then the increase in balance reading in Newton equals the magnitude of the induced magnetic force on Rs. However, balance readings are usually expressed in grams, and so you have to do some simple mathematics to find the induced magnetic force on Rs. What about the length L, and what about the magnitude of the magnetic field? How would they affect the magnetic force? Experiment 4E. Effect of current on magnetic force.
We will find out how the magnetic force on a current-carrying conductor is affected by the current and the length of current inside the magnetic field. Set up a current balance. Adjust the position of the wire until it is balanced. Set the reading of the electronic balance to 0. Switch on the power supply. Vary the current flowing through the wire by changing the resistance of the rheostat. Take the readings of the ammeter and the electronic balance. The reading of the electronic balance gives the magnetic force acting on the current-carrying arm. Repeat several times with other current values. Record the results. Plot a graph of the magnetic force F on the wire against the current I through the wire. How is F related to I? Now pass a fixed current of 3 amperes through the wire. Measure the length of the slab-shaped magnets. This represents the length of the current inside the magnetic field. Then, take the reading of the electronic balance. Record the results. Add 1 and 2 pairs of slab-shaped magnets round the current-carrying arm in turn to double and triple the length of the current inside the magnetic field. Record the reading of the electronic balance in each case. Plot a graph of the magnetic force F on wire against the length L of the current inside the magnetic field. How is F related to L?
First, let me give you some hints about using the balance reading to find the induced magnetic force. An increase in 1 gram of the balance reading should correspond to 0.00981 Newton. In the video, you may still remember there are 2 graphs. One is force against current I, another is force against length L, and they both are straight line that passes through the origin, which tells you the force and I are directly proportional, and force and L are also directly proportional. To control the value of I in the experiment, the rheostat is adjusted so that different currents passes through the rectangular coil. To adjust the value of the length L, different number of slabbed magnets are put side by side, one after another. And in this case, increases the length L. By the way, when doing this experiment, we have to make sure the frame rests horizontally and lightly on the electronic balance. Secondly, the magnetic field produced by the slab-shaped magnets must be perpendicular to the current direction.
We will find out how the magnetic force on a current-carrying conductor is affected by the magnetic field strength. Set up a current balance. Adjust the position of the wire until it is balanced. Set the reading of the electronic balance to 0. Connect a flat solenoid in series with a rheostat, an ammeter, and a DC power supply. Place the current-carrying arm of the current balance inside the flat solenoid. Pass a fixed current of 3 amperes through the wire of the current balance. Switch on the power supply connecting to the flat solenoid. Vary the current flowing through the solenoid by changing the resistance of the rheostat. The magnetic field strength is directly proportional to the current flowing through the solenoid. Take the reading of the ammeter connecting to the flat solenoid and the reading of the electronic balance. Record the results. Repeat several times with other current values through the flat solenoid to obtain different sets of data. Then plot a graph of the magnetic force F on the wire against the magnetic field strength B. How is the magnetic force F on the wire related to the magnetic field strength B?
Experiment 4F. Effect of magnetic field on magnetic force. In order to investigate the effect of magnetic field on magnetic force, an electromagnet is used. In this case, a current I passes through the solenoid. The magnetic field produced by the solenoid is used. To find out how the magnetic force may be changed, note that the magnetic field produced by a solenoid is directly proportional to the solenoid current. Well, in the video we can see, as all we may expect, that the magnetic force is also directly proportional to the solenoid current. In other words, the magnetic force is also directly proportional to the magnetic field applied. So from these two experiments, we can see that the magnetic force increases with the current I flowing in the current-carrying wire, increases with the length of wire inside the magnetic field, and also increases with the magnetic field B. In fact, we find the force directly proportional to all the three parameters. Example 8. Finding magnetic force using a current balance. Instead of using a balance, a radar is sometimes used to measure the magnetic force. In this case, the radar is at P when there's no current flow. When current flows and there is an induced magnetic force, the radar has to move towards X. Then the rectangular coil is balanced again. When the moment produced by the radar balances the moment produced by the magnetic force. Do check point 5 on the next page.